You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Luke Sellers, Gianni Martire, and Alexey Bobrick. Luke Sellers is a graduate student in physics at UCLA, specializing in theoretical astroparticle physics and cosmology. He graduated from UCSB with academic high honors and went on to become a founding member of the Advanced Propulsion Laboratory at Applied Physics. He is the lead researcher on the study Searching for Intelligent Life in Gravitational Wave Signals, Part 1. Gianni Martire is a self-taught physicist, inventor, Y Combinator tech entrepreneur, and former banker who served on the advisory board for Bank of New Jersey. He has developed and sold several tech startups and is now a co-founder and CEO of the physics think tank Applied Physics. Alexey Bobrick is a theoretical astrophysicist who earned his PhD at Lund University in Sweden, an International Physics Olympiad by 19, and author of more than 20 publications. Dr. Bobrick is the Chief Science Officer at Applied Physics and co-founder of the Advanced Propulsion Laboratory. Together with Gianni, he co-authored the earlier covered paper Introducing Physical Warp Drives, which laid the foundation for building practical warp drives, which are consistent with the laws of physics. Remember to subscribe to Event Horizon so you never miss an episode.
Gianni, Luke, and Alexey, welcome to the program.
Thank you for having us.
Now, gentlemen, you have an interesting new proposition for SETI, and that is the idea of searching gravitational waves, which is something that's brand new, something that we only just now can really do after hypothesizing about it for many decades. Now we can look for the possibility of the movement of giant megastructure starships. Could you give us an overview of what that would look like, a huge mass starship?
Yeah, so basically the idea behind the study is that the SETI searches have been going on for decades, and they've primarily involved these electromagnetic searches, mostly for radio waves and that sort of thing. But as it so happens, since 2016, we've been taking a plethora of data, not to do with electromagnetic signals, but to do with gravitational waves. As all of you know, I'm sure, we built the gravitational wave interferometers starting back in 2000. They went online in 2016. Mostly to look for astrophysical sources, so black holes colliding into each other, that sort of thing. But in principle, these detectors can detect anything that's massive and accelerating. So amongst that catalog of potential candidates, we propose that we should also be searching for things that are occurring not naturally, but artificially, which would include these sorts of megastructures that you're alluding to.
You don't find if you don't look. And it's sort of an interesting idea, though,
Exactly.
The idea of creating such a gigantic type of starship that could carry presumably millions of occupants, something like that, or more, larger than Earth, bigger capacity than that. But why not? Physics doesn't prohibit the construction of such a thing, right?
Yeah, exactly. There's no laws of physics prohibiting the objects that we're looking for. The parameter space that we were analyzing in the paper that we recently put out there ranges from objects ranging from around a moon mass to a Jupiter mass. So any megastructure that involves those sorts of masses are things that we would be able to see out to. If it's a moon mass, we could see it out to around 10 parsecs or so, which is past the distance to the nearest solar system to ours. Because if the objects are larger, they're more easily to detect. We could see a Jupiter mass ranging out to almost to the distance of other galaxies.
Now, what hope do we have for the future? In other words, can we get the resolution down to look for even smaller objects, so long as they're close by, with future gravitational wave detection instrumentation?
And if I could just interject there real quick. To your point about the future gravitational wave detectors, one of the more interesting results in the paper that we find is that the signals that these objects are generating, they're more powerful for lower frequencies. So basically what that means is, so the interferometers we have access to now, namely LIGO, is sensitive within a certain frequency range from about 10 to 1,000 hertz or so. But there are future gravitational wave detectors that are going to be more geared towards these lower frequency ranges where these objects are, or the signals that are generated by these objects are more powerful. So in that sense, once these future detectors are built, we'll be more sensitive to these objects as well.
Do you think we're entering an age where we might encounter things like a wow signal in gravitational waves? In other words, seeing something that we don't know what it is. And if such a thing did come through that was a mystery, would we even catch it with the software that we're using to filter the data?
Yeah, and like I was alluding to earlier, I mean, these interferometers were built to measure a pretty particular source. They were geared towards measuring these colliding black holes. In the literature, they're called binary black hole mergers. But as I said earlier, anything that accelerates and is massive is going to be fair game for being detected. So really, there's a very wide array of things we could potentially see with these detectors. It's pretty much up to our imagination of what we could search for. This could include things that are moving under some sort of rocket propulsion mechanism. It could be, some sort of warp drive mechanism that Gianni just mentioned. It could be, some remnant from the Big Bang that might be really interesting from a fundamental physics point of view. So really the catalog of things we could potentially see is not very limited. It could be a very wide range of things, which is what we think makes it so exciting.
If I may add, one of the the paper got quite a lot of press coverage, and so in press somebody expressed the idea that it might be like a sign of Death Star, like from Star Wars. And it's actually fun because LIGO actually manages to put limits on how many Death Stars can there be in our own galaxy, right? And so and in the future when the new detectors are built, we can say how many of them are in any galaxy, like in galaxies far, far away too. So it's actually quite exciting, I find.
Exciting in one way, but in another way, finding something like that, say a nickel Dyson beam or something that mimics the sci-fi idea of a Death Star, all of a sudden there's somebody in your galaxy that can obliterate a planet if they want. So it might not be it'll be exciting, but it might not be that comforting ultimately. And that's one of the things that captivates my own mind is, so you say you see something anomalous and you're like, this kind of looks like it could be a giant Rama ship, as you guys put it in the paper, but it could also be something else. But whatever it is, it appears to be due to the activities of an alien civilization. And I think that's really where the real excitement comes, is when you don't know what they're doing, right?
Yeah, exactly. And I suppose if it's a Death Star, it's all the more reason to start looking, just in case.
Yeah, so one of the main things that our paper really points out that, SETI and LIGO should really be best friends. Because when you think about it, we already have the equipment, LIGO's already there. We concluded these experiments in 2015 and 2016. And, it's with using LIGO first to see if there's any gravitational wave anomalies, then you can use SETI to see if there's any radio anomalies. And you can further inquire and further see, is this a new natural event in physics and in nature that we just don't understand, that we didn't know was possible in the universe? Or is this possibly an advanced civilization? So because you have a gravitational wave anomaly doesn't necessarily mean you found ET. So teaming up with radio waves and gravitational waves, I really think it's a perfect marriage. And it's already there. And in terms of the expense, it's just analyzing the data, and the data is already there. So it's just to really now building the machine learning software and tools, and that's where we're really focusing here on applied physics to really analyze the data at an efficient rate and effectively, because of course it's very noisy, and these signals are very minor. So it's really clearing the noise and really working effectively from there.
Right, I was sorry if I could just add on to that real quick. And kind of along the lines of what Gianni was saying, the fortunate coincidence is, these detectors have already been built and they're building bigger and better ones in the future. Not even for the purposes that we're talking about, but also for, the concerns of the fundamental physics community. Like they want to see signals produced in and around the time of the Big Bang and that sort of thing. So, the artillery for our ability to do more and more sophisticated searches of the type that we propose is coming, even if it's not necessarily geared towards the particular use case that we're suggesting. So it's kind of a fortunate circumstance that what we have in mind and what the fundamental physics community is going for are pretty symbiotic in that case.
Now, does this provide us, and anyone feel free to answer this, does this provide us a potential probe into studying the nature of dark matter through its gravitational interactions?
Yeah, I can comment on that a little bit. I'm not entirely familiar with the literature, but there are definitely quite a few sources that are sort of brainstorming the potential things that you could see with the next generation of gravitational wave detectors. So not just LIGO, but the future generation, including LISA, Desigo, Tianquin, that sort of thing. And amongst them are definitely dark matter candidates. Like, for example, I think in the early universe scenarios, which those sorts of detectors would be probing, there are potential dark matter formation mechanisms that people would be interested in observing and that sort of thing. So that kind of goes into what I was saying earlier about, this technology being of equal interest to the SETI community, as you guys say, but also the fundamental physics community, because they can answer questions about both SETI questions and fundamental physics questions involving dark matter, like you say, but also dark energy and things like that. So in that sense, it's really exciting on two fronts, really.
Now, say you get a candidate for a Ramacraft, huge spacecraft. What could we determine from the characteristics and the signal of, can we tell how fast it's moving, and can we tell from what direction it's moving and where it's going?
Yeah, so these are all questions that can be potentially answered by the detector where the signal is registered. So right now, when LIGO detects a black hole merger, for example, they can tell to a pretty substantial degree what direction it's coming from based on the fact that we have multiple LIGO type detectors. So we have two LIGO detectors that are one's in Washington, one's in Louisiana. And then we also have the Virgo detector, which is in Italy, and Calgro, which is in Japan. So because we have multiple detectors, that allows us to kind of gauge what direction these signals are coming from. So to answer your question, whether or not the signal is measured by the current interferometers, the ones I just mentioned, or the future ones like LISA or Desigo, the Big Bang Observer, etc., there would be mechanisms in place that would allow us to measure like the direction and where it's coming from, for sure. In terms of what other aspects you could determine from the signal, so that all comes down to how the parameters of the trajectory of the object contribute to the signal. So for example, the signal that you get is going to be dependent on the mass, for example, the change in velocity, the distance to the object, etc. So you may very well be able to differentiate all of those parameters, or you may be able to, for example, know like what sort of combination of mass and change velocity is present. But basically, further differentiation is going to require more detectors, most likely.
Could you send a message? In other words, say a standard like what we would look for in radio SETI. Could you use such an object to send a gravitational wave message, a contact message?
Sorry, by object, do you mean the detector or the Ramacraft?
The object itself. So the Ramacraft, could you move it in a very characteristic way in order to announce that this is an alien saying hello? In other words, a contact signal.
Yeah, absolutely. So what you're talking about in the literature is usually referred to as a gravitational wave beacon. So it's pretty much exactly what you say. Basically, a device that's intentionally geared to create a signal that's observable far away. And if you are going to do that, then using a gravitational wave as opposed to, for example, electromagnetic wave is a reasonable thing to do because, for example, gravitational waves don't really collide much with things as they travel through the cosmos, whereas EM waves definitely do. They pass through objects much more easily, basically, is the point there. You could, what object would you use to make such a beacon? Basically, anything, like I said earlier, anything that's massive and accelerating is what you'd want to use. So if you wanted to make the largest signal you would want the largest mass possible. So, I mean, that very well could end up being some sort of moon scale mass or Jupiter mass or something like that.
Although I might maybe add that, so sending a gravitational wave signal like that is possible, but it's also very hard. So it's an effort comparable to like on Earth. Like, you could send a SMS, but you could also launch a rocket and send an equal, value signal. So like, how to say? I mean, it's comparable in complexity. So like launch a rocket versus just send an SMS, right? So there too, right? So it's, sending a ship that accelerates to the speed of light almost and then accelerates. It's very hard. So, I mean, but it's possible.
Yeah, it's that's a very fair point. Though I suppose if you're trying to send signals over the scale of like parsec or kiloparsec distances, then the options that you have of something that would reach that far might be limited. So it could be the case.
Yeah, so maybe there's a sweet spot for how far it can be sent best.
Yeah.
But even if it's just within your galaxy, it might be worth doing, especially if you're a civilization that has effectively unlimited resources and you're a Kardashev type 2 or type 3 civilization that can move stars and do things like that. Well, this suddenly becomes viable. It'd be hard for us to do, but not somebody that's a billion years older, you know?
Yeah.
But it's super cool. Yeah.
Yeah.
Sorry.
Yeah, for all we know, it might be the equivalent of sending a iMessage, as Alexey was talking about.
Yeah, you can also kind of get in touch with everybody in the galaxy who can detect gravitational waves, which is like a very good filter for like developed civilizations, right? So it's actually quite an intelligent way to search for intelligent life.
Yeah, it's a way to get to the cool kids club in the universe.
Yeah.
You weed out the radio riffraff and you look for the people that can really do something.
Exactly.
And very confirming, because if you get a gravitational wave signal and they swing a radio telescope and pick up some narrowband signal emanating from the same place, then you've got a pretty good idea that you're seeing an alien civilization. So it actually would serve to confirm it, right?
Yeah, it's super valuable to have multiple ways to confirm the occurrence of some phenomena. So if you can measure something with electromagnetic waves and then see that the same thing is being told by the gravitational wave story, then that's the perfect scenario, really. So more data is always better.
Now, could you search combinations? In other words, could you have a mixed bag where you see a gravitational wave signal, so you turn the radio telescope to it, you see a radio signal, and maybe even a visual signal, and take it as a whole, all three of them together, could you find some sort of message using multiple mediums?
Well, this is actually the promise of the multi-messenger astronomy. So astronomers have been trying to detect neutron star mergers or black hole mergers through a variety of ways, like optical, X-rays, gamma rays, and gravitational waves. And the whole community has been extremely excited about it. So, I guess maybe it's we're talking about maybe something like multi-messenger SETI, which actually would be just as exciting and as informative.
And useful, because one thing that's always bothered me about SETI is that, well, maybe aliens don't put all of their eggs in one basket because that lowers the chances of being detected. So if you really want to be seen, send it out on multiple channels that are complementary and build your message that way and try to communicate, some science message, a description of the hydrogen atom or something that alien scientists that they're trying to contact might be able to decipher. And then that's the real way of sending messages in the universe, is trying to make some kind of universality that everybody understands, which is a big trick because, how do you talk to an alien? In this, though, with gravitational waves, are there limitations on what you could do? In other words, yes, you can send out a message that's very likely going to propagate and not be interfered with. But at the same time, do you have the nuance that you have with radio? And is this going to be as complex as the radio spectrum is?
Alexey could probably speak to that a bit, but...
Or I can rephrase it. Can you actually send data this way as efficiently as you could with a radio signal, a satellite downlink or something?
The signals are generated by different physical mechanisms, but they're essentially the same thing. They're both just one-dimensional pieces of data. So, you could have a sine wave, you could have whatever, you could have some envelope AM modulated type thing. You could really have whatever you like, or whatever you might have in the AM case. Whether or not it would be more difficult to generate in the gravitational case very well could be the case. Like to what Alexey was saying, it's obviously easier to send a text message than to generate the equivalent text message with some sort of gravitating body. But in theory, they're essentially the same thing. So.
Well, there's one thing though. So if you try to send a radio wave through the galaxy, there's a lot of interstellar gas in the galaxy and plasma that attenuates and basically, absorbs the radio waves. They cannot actually travel too far. And gravitational waves do not care about that, so that's a big benefit in that. So we cannot really see very, very far in the galactic disk through radio because of this intergalactic plasma, interstellar plasma. Sorry.
Yeah, that's another important point. So what Alexey is saying, another way to quantify that is that sort of the best reach for SETI electromagnetic searches right now range up to around 10,000 stars or so, but for what we were looking at in the paper, we could see the objects that we discussed up to like, I don't even know how to express the number, but like 10 to the 11 stars or something like that. Pretty much like most, if not all stars in our galaxy. So it's
100 billion.
quite the boost in range. Granted, it's for more extreme objects, but to have that complement, we think is going to be really valuable.
And there was yet another thing, right? So like with SETI or with radio, you have to really know where to look for, because like in radio, you just have a little beam into which you have to point your telescope, and then you maybe can detect something. In contrast to that, gravitational wave observatories can see all the sky at once, and they operate continuously, and they don't have to even be distracted from their operations of like science, like from their science goals and such. So that is an advantage for gravitational wave communication. You don't have to like look at all small patches of the sky like with radio telescopes. You can just get all at once.
Yeah, that's a big concern in SETI is, we're talking about things like PanoSETI and this idea of all sky surveys and things like that, but you've already got that with gravitational waves, and you're just searching for data that's already been taken for science purposes. So it's sort of low-hanging fruit. I would also point out that while it may seem a huge undertaking to create a giant megastructure with a massive Jupiter, it also has to be said that nature already does this for us. It creates planets and black holes and neutron stars and all this stuff. So we already have the objects needed to create the signals. We merely have to arrange them. So do you anticipate that another avenue of this might be searching for really weird juxtapositions of black holes, black holes arranged in a Klemper's rosette or something like that, that in itself signifies, without the need for spacecraft, it in itself signifies an astroengineering project by an alien civilization?
Well, there are studies a bit like that search for unusually looking stars that could have signature of Dyson spheres built around them, for example, that dim periodically in a weird pattern or something. And that's also a useful way to search for like mega technology.
Yeah, like I was saying earlier, the catalog is pretty much up to anything that is massive and accelerating. So all these sorts of contraptions that you're mentioning are fair game for detection. Like, for example, there's another study that was published, I'm not sure how long ago, but it basically involved a Jupiter-sized mass that's orbiting the black hole at the center of our galaxy, Sagittarius A. And the study basically showed that such an orbiting mass would be detectable by LISA once LISA is constructed. So pretty much any sort of orientation of these sorts of bodies is going to be detectable. Granted, searching for them is like doing the data analysis to search for all these sorts of different signals might end up being fairly computationally costly, and you might think that you'd have to sort of pick and choose what you want to search for, because at the moment, the way that these gravitational wave searches work is that you have to sort of apply these filters for every data set at every time you go through it, so they can take quite a while. But what might augment that is if you sort of front load the computational cost by training a neural network to search for all these sorts of signals. And then if you, which isn't really done in searches now, but if it is in the future, which is something else we're working on, then you might be able to search for, any sort of signal, which would encompass what you're talking about.
Interesting times. And I think that as we move further into the study of gravitational waves, which it's in its infancy right now, but as we move into it and gain resolution, we're probably going to see a lot of stuff that we don't really, just like with radio, that come out of the noise that we don't really know what it is, and I'm looking forward to that. The mysteries that are going to come out of it could open up a whole new dimension of above and beyond visual and radio astronomy. Gentlemen, thank you for joining us today, and I look forward to your next paper, and I hope you all come back.
Absolutely. Thanks for having us.
Thanks for listening. I am futurist and science fiction author.
Wrong channel.
No, it's not. Thanks for listening. I am futurist and science fiction author John Michael Gauthier, currently hosting Event Horizon and wondering where Anna actually came from. One day I had a tablet computer, the next I had a boss. Very disturbing, and be sure...
And that's enough of that.
YouTuber forever! Like, subscribe, and hit the bell!
Sell out.
What?